per unit time times the area of the surface patch.
Maybe I just come off the camera.
That'll do it. On the other hand, suppose that the fluid is not coming directly at the surface. Suppose you have a situation like this, where it's coming at an angle. Okay. Well, in that case, because it's coming at an angle, it's almost as if there's actually a smaller area that the fluid is passing through. Effectively, what you're doing is, if this is the normal vector to the surface, then what you really need is, when it's dead on, it's going to be the magnitude, but really what you're going to get is dot product with the normal vector times the area. And n, that is the unit normal vector. It has to have length 1. So suppose that the fluid is being directed perpendicularly to the surface, or in the perpendicular direction, it's going this way. Well, you're not going to have any fluid passing through the surface at all. And that's reflecting the fact that the dot product will be 0. So flow along the surface, so not going through it, you're not going to get any fluid passing through at all, whereas if it's dead on, then the speed of a fluid times the density times the area is the rate of change of how much fluid is passing through. All right. So what happens in this case is this surface integral, what is called as the flux, so it's an indication of the amount of fluid that's passing through the surface per unit of time. So what you can think of is we're applying this formula on all these small patches, and then we're to see how much fluid is crossing each patch, and then we're adding up the results. So this is one physical interpretation of an integral of a vector field over a surface, which actually is one interpretation that happens to come up in my own research. Another is if F is an electric field, so then the surface integral is called the electric flux across the surface S. And then there's one more, which is important to mention because it's something that we'll be coming back to in later classes. Suppose that your vector field is minus constant k times the gradient of some function u, where u represents temperature. So it's a function that gives you the temperature of an object at any point within the object. K is constant. Of thermal conductivity. So in this case, the surface integral of this vector field, so that's called the heat flux. Across the surface S. So it measures how much heat energy is passing through the surface per unit of time. Because think about it, if you have a solid object, then what you can do is say that the rate of change of of a temperature within the object, the total amount of heat energy within the object that's rate of change with respect to time is equal to the amount of heat energy coming in. So the net flow of heat energy coming in that includes energy coming in, energy coming out, plus the effects of any heat sources that are within the object that are simply adding more heat energy in. So you end up having this conservation law, if you will, and if you describe it in terms of a surface integral like this, and then an integral over the solid of du dt, we actually come up with one of the most important partial differential equations in all of applied mathematics, which is the heat equation. We're not ready to do that yet, because at the very last section of Stewart, there's a theorem called the Divergence Theorem, which we need. But once we get to that point, I'm actually going to derive that equation. So you can see how all these things come together.
So why is it the most important applied mathematics?
Well, really describes so many things, not just dissipation of heat energy. Any process where there's diffusion or dissipation going on, which is true of energy, for instance, can be described using an equation like that. So really, it's called the heat equation, but more generally, it's called the diffusion equation because diffusion occurs in such a common phenomenon. Okay. So, preview of coming attractions. Okay. So now is when you can tune back in, because I'm going to do some examples. Hey, try to be realistic, you know. All right. Okay. See how we're doing on time. Okay. All right. There's really two examples I want to do. Only one of them's in the notes. But I should have time for the other one. Okay, so this is 13.7, number 22. Okay, this one can actually be done a couple different ways.
Do that in Hardy Street.
What?
Do that on Hardy Street.
Oh. Alrighty. So we have a cone. This has come a time or two before. Z is equal to x squared plus y squared. Where Z is bounded by 0 and 1. So it's just that portion of the cone. So that is our surface that we're going to be dealing with. And we're just going to be dealing with the cone itself. We're not including the top of this. Okay. All right. So the vector field we're going to deal with is x, y, z to the fourth. So we need the integral of this vector field over this surface. Now, there's a couple different ways that we can do this. Now it's tempting. What? Oh, that?
Yeah, that.
Yeah.
That's what you can store here.
Tell them they just need to be pushed up one time.
Now it's tempting to use the fact that this surface has a relatively simple definition. It's the graph of a function of two variables. And we could use that. But the fact is...
Okay.
Okay. No matter how you go about this problem, at some point you have to involve polar or cylindrical coordinates. So we'll just involve cylindrical coordinates from the outset, and then that will make things a little easier down the road. So you can get the pain out of the way immediately, or you can delay it. That's your choice of this problem. Okay, so parameterization that we'll use is that x will be u cosine v. So it's like polar